Good afternoon. My name is Christopher Maldonado, and I am an undergraduate material science and engineering student at the University of North Texas. My project for the summer with ARL concerned XY gradient composition and 3D printed transparent ceramics. And the goal here was to work on further expanding additive methods of ceramic composites through the use of using gradient composition printing. And as well, for our specific materials that we chose, yttria and magnesia, we were looking to see how the change in composition would affect the infrared properties. For our project, we ended up using an additive method known as direct ink write, which is where you take a nozzle and a nozzle tip with a syringe and a source of pressure, such as air or a spindle, to help extrude material directly onto a substrate or surface. And in order to create these actual structures, you have to use something known as a slurry for these types of additive methods, in which a slurry is a particle suspension where you have ceramic particles within a solution held in place. And these slurries are typically, think of toothpaste in terms of consistency, but instead of it being something you brush your teeth with, it's something you're using to create ceramic structures with, such as rectangles or squares or other geometrical structures. And in order to formulate these ceramic composites, we had to use we started with a steric design for the slurry system. And a steric system essentially uses polymers to physically help separate the particles in the solution. You would coat every particle essentially evenly with a coating of polymer to help physically separate the particles and create an even dispersion for the system to be able to flow smoothly out through the nozzle. However, we encountered a couple limitations with this type of system. Namely, one, the solvent we were using was drying way too quickly since ethanol has very high vapor pressure at room temperature. Hence, as soon as we were printing, it would turn directly into a solid instead of maintaining some kind of liquid behavior. Secondly, the actual flowing behavior of the slurry was inconsistent. At some portions, it would flow smoothly, and others, it would flow out in chunks. And thirdly, we weren't able to pack as much ceramic particles into the solution as we would have wanted, which ends up helping out later on when we get to post-processing. And in order to address all of these problems, we ended up transitioning into an electrostatic system to help the particles disperse. And an electrostatic system essentially uses the surface charges on the particles themselves to help disperse the solution evenly. Think of every ceramic particle like a magnet, but with every magnet, every time you have two like charges, two like polarities, you will get a repelling force. The same idea works here, in which we were able to increase the amount of positive charges within the solution by making adjustments to the pH to help create a greater dispersing force within the solution. And through using this electrostatic design, we were able to solve all of the previous problems we had with the steric system. Namely, with this use of the dispersion force, we needed less solvent. Therefore, our slurry was able to maintain liquid state for much longer periods of time. Secondly, it was a much more consistent flow state of transition between liquid to solid behavior and vice versa when printing. And lastly, we were able to increase the solid loading from a 15 volume percent up to a 35 volume percent, over doubling the amount of particles we were actually having inside the slurry. And we were able to use this design to actually print a multi-layered sample where we transitioned from a 100% yttria magnesia premixed composition to a 100% magnesia composition, all within one layer. And once printed, we were able to take this sample and we were able to start trying to do preliminary post-processing, where we would bind or burn out the polymers. Since at the end of the day, for our application, we only want to have the ceramic particles remain. And our application is actually optical infrared applications. We want to create a transparent ceramic of just pure ceramic particles where the ceramic particles you're able to visually still optically see through them, but they are able to deflect or interact or dampen infrared waves from penetrating through. And that's what this last portion of the project would have been, post-processing the sample to get it from the green body or printed state to that actual transparent state, burning out the polymers and then using further heat and pressure to densify the sample and create a transparent ceramic with varying infrared properties across the surface. And that's the step that we would do next for the project. We would do further post-processing and analyzation of the surface, not only of the composition, but of the infrared properties. And further optimization of the slurry design and printing parameters and the post-processing would allow us to create a highly tunable, optically transparent, high-temperature ceramic capable of deflecting infrared waves. Thank you.